Hey, hey, hey. It is 2:05 UTC, Coordinated Universal Time, and welcome again to Astronomy Daily Live. So you can call me Cosmic, and this is just a daily live stream where um, a growing number of friends come together who share a common passion for the science of astronomy and everything that um, um, encompasses, which is pretty much everything. When I was a kid, I was extremely uh, fascinated by everything. So it's like, how, what what do I have to do? What sort of category do I have to get myself into in order to study everything? And the obvious choice was astronomy. So here we are again. This is just a casual, fun get together of friends every single day to, turn off the TV, forget about the news for a while, and think and talk about astronomy until, well, at least until uh, our time is up. There really are no time limits per se, but um, I do respect your time and greatly appreciate you coming in, and so I try to keep it to, you know, about an hour or so. Sometimes it's a little bit more. Try not to make it any time less. But um, so yeah, here we can talk about pretty much anything that anybody wants to. Um, uh, we can do Q&A. We can talk about telescopes. We can talk about gear. We can talk about cosmology. We can talk about binary stars. We can talk about regular stars. We can talk about uh, uh, galaxies, different kinds of galaxies, different kinds of planets, different kinds of moons, um, exoplanets. We can talk about the spacecraft that are collecting a lot of data. We can talk about um, all the instrumentation on the ground. What do astronomers do? How do telescopes work? What kinds of telescopes are there? What telescope is best for me? Um, you know, how do professional astronomers write papers? How do they do their research? The questions just go on and on and on and on. So if you're new to this channel, make sure to subscribe, hit that notification button, and you will be told when this live stream goes live. If you want to be part of the panel down here, right? I've got 10 slots available. This is called a Google Hangout. So we're supposed to be hanging out for some time talking about astronomy in this case. And if you want to be part of the panel, let me know. You can shoot me an email, cosmiclettuce@gmail.com. And as soon as the stream goes live, I will send you a link and we can link in. Now, I have yet to have a panelist on this show, so I think it'd be very, very cool to give that a try, see how that works. I don't know I I don't know how that is going to work out. Um, but yeah, I'm anxious to find that out. Also, down um, in the description, you'll see links to my Discord server and to my Twitter account and to actually this YouTube channel as well. So yeah, if you're new, just coming in, make sure to subscribe. If you like what you're seeing, hit the thumbs up. If you don't like what you're seeing, hit the thumbs down. Make some comments. I always like criticism, constructive, I would hope. I'll definitely respond to all those kinds of things. So yeah, let's talk astronomy here for a while. So I've been out um, collecting calibration data for tonight's observations. I'm trying to characterize my telescope and CCD system. Now I've got a Celestron Next Star 8SE telescope. It's a 0.2 meter telescope, otherwise known as an 8-inch telescope. I have a SBIG ST7 ME. Is it ME or XE? I don't remember. I think it's an XE, ME, something like that. 16-bit CCD camera, and in order to have any valid observations at all, the the most important thing that I have to do, even more important than taking the data itself, right, is taking calibration data. And there's basically two parts to that. There are um, um, dark fields, which are exposures at different times uh, with the shutter off and or the telescope closed. So the CCD isn't actually seeing any light. What it's seeing, well, light from the sky, light from stars, light from a target. The only thing that it's seeing is uh, uh, um, sort of the electronic noise, the thermal noise of the CCD itself, and that's like a DC offset. It's like a pedestal that all the other data sits on top of, and so I don't want that to be a part of my final measurements. So I have to collect that data at different exposure times that correspond to the exposure times um, of either my science data or my other calibration data, so I can subtract those darks off. I want to remove the pedestal. And so the other piece of calibration data that I have to take are called flat fields. And flat fields are a measure of gain. So, and there are sort of two primary um, pieces to that. The first is um, it measures the optical system itself, any kind of flaws in the optics, any pieces of dust, um, anything at all in the optical path. So that's the path that goes uh, through my um, entrance window at the front of the telescope to the back of the telescope where there's a primary mirror that's curved. It's concave like that. That light focuses to a secondary mirror that is also at the front of the telescope, and that mirror is convex. That reflects the light down through a hole in the primary mirror to my camera, which sits uh, which sits at the back of the telescope. And so one of the things that the flat field does is it measures any kinds of imperfections in the optical path, vignetting, as I said, pieces of dust, whatever, right? The other thing that the flat field does is it measures the sensitivity of the CCD pixel by pixel. So every pixel on a camera is a unique individual that has its own sensitivity. Now, they try to make these CCD cameras so every pixel is more or less sensitive in the same way, but that that's impossible. So the flat field also measures the sensitivity of the pixels, and those those are wavelength dependent. So if I were to be observing, at a certain wavelength or band passes, like R, G, and B, okay, I would have to take flats for R and G and B because the pixels are not only sensitive to light, um, just light, but they are sensitive to different wavelengths of light. Now, in my case, I'm I'm currently not using any filters, so I just have to take one set of flats, um, and flat fields are a measure of gain. So uh, uh, instead of a dark field, which is just a DC offset, so it's just a subtraction, right? The flat fields are a division. So I have to normalize all these. So, all all the data values fall between 0 and 1, and usually they're all up really 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 close to 1. um, there's usually a 4 or 5% um, difference between sort of the highest gain and the lowest gain. And flat fields um, get divided out. So in my in my science data, when I go take my science data, okay, what I'll do is take the data, right? Then I will and um, let's just say that it's like this, right? So then what I do is I subtract my darks like that, and then I apply my flat field like that. So in the end, I have a reduced image that is just the light that I want to measure. Um, just the light from the sky and from my target, just the light that is going through the telescope, not being affected by any of the electronics, not being affected by any um, anything in the optics. So if you don't have calibration data and you want to do science, um, then you might as well just pack it up and go home because there's no point. There's no point. And last night, that was the case. I was having some problems um, with my electrical power here, and so I wasn't able to take very good calibration data last night. And once I realized that, it's like, screw this. There's no point. There's absolutely no point in um, trying to um, continue. There's no point in actually staying up late and collecting actual science data. Absolutely no point at all. Now tonight's data, uh, calibration data is probably some of the best I've gotten yet. So I'm pretty anxious to get going with tonight's observations. Yes, there is a full moon. I don't even care about that because what I'm I'm trying to do is just characterize my system. How well does it work? And can I do things, you know, during the observation to make sure that it works as well as it possibly can? So I'm sort of, on a learning curve as well, with all of this. Although, I've done this quite a few times, for different systems. So, I sort of have, a series of recipes, that I can go through to figure it all out. But every situation is unique and challenging and all of that. So, yeah, solved last night's power problem. It turns out that my um, uh, um, my common line, the white wire, uh, my common power, uh, turns out wasn't properly screwed down inside of the breaker box. And so last night, I was losing power just over and over and over again. I mean, I'd be running like this, not this well, but I turn the laptop on, I get everything going, and then lose power for like half a second, right? And that would just shut me completely down. It shut down the computer that I'm using to run the telescope and um, the CCD camera, all of it. It was just total, just a shit house. And so gave up, frustrated, and packed everything in. Luckily, I live in a location where it's all I have to do is walk outside, and I've got the most awesomest sky possible, right? Given the conditions of a full moon, um, it's not incredibly dark, but actually, when the moon is full here, it's almost, not quite, but it's almost like daylight outside. It's very, very bright and very, very, very cool. So yeah, got up this morning, still having power problems, right? Got into my office here, started doing everything, started losing power right away. And it's just like, it's insanity. It's insanity. So I went around, all these, uh, all of these were on one circuit. So I went around and I checked all the outlets to, wiggle them around, make sure that there wasn't any funny noises, doing all sort of the normal things, that one would do to try to diagnose these weird, stupid problems. Didn't see a thing. Didn't see a thing um, with the outlets at all. So it's like, okay, I'll look in the breaker box. There's not going to be any problem there, but I'll look anyway, just in case. You never know. You got to be thorough. um, so opened up the breaker box and immediately heard and saw sparks and noises. So I looked down and immediately saw that I had just, I don't know how these kinds of things happen, but they do. I had a loose wire, a loose common wire. Um, so I turned off that breaker, checked the wire out, make sure that, it wasn't completely destroyed. Had a little bit of melting of the insulation, not a problem, not a big problem at all. Stuck the common wire back into the common bus, tightened it down, made sure it wasn't touching anything else. Um, and here we are, running power. I've got the telescope and the computer outside running. Um, the CCD camera is thermoelectrically cooled. I've got it set to -5 degrees Celsius. The these cameras, I think, can cool down 40 degrees below ambient. So you know, I, it's uh, it's currently probably ambient air temperature is probably maybe about 20 something like that. I'm asking it. I'm asking it to go to -5. So that's just a 25-degree difference. No big deal. The the CCD can handle that kind of workload. Yeah, yeah. I'm glad that nothing else worse happened too, because the worst thing in the world is to have these power things where they go off and on and off and on. No computer in the world likes that, and CCD cameras definitely do not like that at all. So yeah, that was you know besides not getting my calibration data, which means that the whole night is just shot. Right, this is completely shot. So besides not getting my calibration data, I'm also freaking out because uh, this thing is messing with my computers and my camera, and you know don't want that to happen. But all is well. Um, as I said, I successfully took some really, really, really nice calibration data tonight, and now I still have to clean my optical path. I've got some serious dust somewhere that I really do need to show you guys what a flat field looks like. Um, I've seen worse. I've seen better. So I definitely need to get one of those little um, air blow things and blow around in there. There probably isn't any dust inside of the telescope tube because it's sealed. Um, but there's probably dust. Probably where I'm seeing this dust is actually on the front of the CCD camera itself. There's a little window that it has to look through, um, and my guess is that most of the dust is on that. So, but yeah, I'm not too worried about that. I was looking at my flat fields from a couple of weeks ago, and as I said, I'm seeing like a 4 or 5% variation um, in terms of the gain. So I mean, it looks really really bad on the screen. When you do a little bit of stretching, displaying the image from like the minimum to the maximum, it's going to pop all those imperfections out. But I actually want to see that um, because it gives me an indication of what the gain is and all that. So tonight is going to be nice. As I said, I don't really care about full moon at all. Even if I was taking science data, the only thing that the moon does is it brightens up the sky, so you can't see as faint um, on a target as you might otherwise. But I'm just looking at stars. I'm probably going to be back on M41, M46, maybe M67. Um, yeah, I need to collect a lot of data. The more data I have, probably the better. off I will be. So that's sort of tonight's program, is to just basically just sort of sit on some open clusters that have a nice variety of stars that are bright enough, to see. And I'll have the moonlight, so I won't even need a flashlight. And yeah, yeah, and temperatures are nice. Hopefully the wind won't be a factor. It shouldn't be. Um, I've been uh, I've been pretty impressed. Let me share my screen. I've been monitoring uh, these these two weather sites. The the one that I've been using for forever um, is called cleardarksky.com. Let me share my screen here. It's called Clear. Oh, not Clear. Clear. Cleardarksky.com. And so when you go to this site, the first thing that you want to do, unless you want to read through all this stuff, is just go to Clear Sky Charts, thusly, and then you can. There's a bunch of different ways to sort of find your location. You can type in your latitude and longitude if you want, um, or you can go by state or country, whatever. All right, so I'm in southeastern Arizona, so the closest sort of location so far to me is the Chiricahua Astronomy Complex, CAC. And this is what it's saying that my weather should be like for about the next 48 hours or so. So, as I said, I'm in southeastern Arizona, so I'm 7 hours behind UTC. So it's 2:32 UTC on the 30th of March, 2018. So that puts me at 7:32 p.m. on the 29th of March, 2018. So the clear sky chart is saying, okay, should be clear. Transparency should be above average. Seeing should be average. Not very dark, right? Not very dark because the moon is out. So not incredibly dark. Obviously not as bright as during the day, right? But still not very dark either. And the next several days, that's how it's going to be. Um, Wind, they say, is going to be pretty windy, pretty windy, but low humidity, right? Low humidity, temperatures in the 50s. That sounds about right. But what I found another site um, that actually I've been monitoring this pretty closely. This one's called clearoutside.com. Clearoutside.com. By the way, I'm indulging tonight in dihydrogen oxide. Yes, H2O tonight. So that's just to keep me awake. So what you can do, you can enter. I'm going to enter my approximate latitude and longitude. 0 and get the forecast for that. And come on. So this is sort of a different format. This is just showing the next 24 hours here, right? And it's showing pretty much exactly the same thing, right? Here's the local time. Here's the total clouds. So looks like I'm going to be clear. Look at the wind though. See, the wind is different. Clear dark sky says it's going to be windy tonight. Clear outside says it's not going to be very windy tonight. And so far, my observation is that it is not very windy tonight. Temperature, as you can see, this says it's going to dip down into the single digits Celsius. No big deal. The humidity is typical desert. It's dry. So we can also look at tomorrow's just to compare it. So here's tomorrow's forecast. And as you can see, they are showing that it's supposed to get cloudy here again, while I should have kept clear dark sky up. Clear dark sky. I did it again. Clear. So this, sky conditions is one of the things that every astronomer, at least ground-based astronomer, has to deal with. Space-based astronomers have to deal with other things. So clear sky chart is saying that tomorrow is supposed to be clear, okay? But clear outside is saying that tomorrow, and actually starting tonight, it's supposed to get cloudy. It's supposed to be cloudy all day tomorrow. So it looks like just high clouds. See, these guys are saying that it's high clouds. It's not low clouds or medium clouds. It's high clouds. So just that high cirrus stuff. So see at 8, 9, 10, 11, 12 on the 30th. This is showing clouds. And at 8, 9, 10, 11, 12 tomorrow, look at it. It's showing clear. So I don't know. It is showing, yeah, I mean, it's even showing above average transparency. So, got to compare these two and see what's going on. This is also saying that the wind, there's not going to be much wind tomorrow either. What's this one saying? This one's saying, no, a little bit of wind. Anyway, the funny thing is that I've been relying on this clear sky chart on clear dark sky for years and years and years. These are what are used at major observatories, and what I'm seeing is uh, not only a difference between this and clear outside, but I'm sort of noticing that clear outside is a little more accurate. So we'll see if it gets cloudy here tomorrow. Um, I should wake up in the morning and see high thin clouds. Now, one of the nice things about observing tonight, I mean, it's a nice thing and not a nice thing, is that with the moon out, I'm going to be able to see, I'm going to be able to see any high thin clouds in the sky. So I'm hoping that there aren't any, but if there are, I will definitely see them, especially with backlit by the moon, and they'll um, pop out like crazy. So at least I'll be able to see them and avoid them. That's one of the problems of being at a very, very, very dark site, is that when there isn't any moon out, any clouds, any cloud, doesn't matter if it's a high, medium, or low cloud, you can't see them. They uh, they just look like black patches in the sky. And if it's that thin stuff, it's almost impossible to see it at all. The only way that is the next day or the next week, when um, you're looking at your data and it's it's just total garbage, right? So here I got to grab my chat again, so I'm not missing out on just the wildness over there. Cheers. So I noticed that Tony Darnell with Deep Astronomy uh, did a video on the galaxy that they sort of inferred from observations has no dark matter in it. And I sort of looked at that paper last night during this live stream, just sort of briefly, looked at the abstract. I don't remember if I pulled it up and actually looked at the actual paper itself. It's, it turns out that uh, supposedly, at least, for normal galaxies that have dark matter in it, there's some kind there's this ratio, um, and when they observed this galaxy, that ratio was much reduced, and so the inference there is that there is no dark matter. I think, for one, I think that dark matter is sort of a stretch in and of itself, um, to make a further inference about uh, this ratio. I don't know. That's a little bit of a stretch too, but that's okay. That's okay. I mean, as I said, my attitude is skepticism and open-mindedness. So I don't close the door on things just because I'm skeptical. I think that's being a good scientist. So look at things hard, look at things with a skeptical eye, but be open, be completely open, have that door wide open. Take a good look at all of this stuff. I think that's really, really important. And I think it makes it really, really fun to investigate stuff because you can dive really, really, really deep um, into things and at least understand where these um, where these people are um, coming from. I think it was a dwarf galaxy again. So you got to look and see how are they making the observations, what data are they looking at, all of that, and it's really really fun, really really cool, and don't just rely on sort of the headlines and the news reports on this stuff. My recommendation, even if it's even if it's really really hard, is go to the source, find the paper, read the paper. Um, that, as I said, is a launching pad to allow you to go off in lots of different directions. There will be references to, you know, statements made, um, you know, about the observations, about, what what's sort of the history behind, coming to this kind of a conclusion. It's all there. It's all there. And yeah, I mean, it's hard, um, but that's science. That's science. Science is not just collecting data. Science is the whole, it's a whole process, right? Data collection is a very important part of that. But if you are just collecting data, you are not doing science. You are participating in the scientific process, but you're not doing science. You're not a scientist if you're just collecting data. You're a data collector. That's all you are. Um, yeah, I mean, and again, not to knock that at all because that's extremely important, extremely fun. And if that's what you want to do, then that's very, very awesome, very important. But you're not doing science. Definitely, definitely not. Science is an entire process. I should grab that graphic again. It's been a while since I've gone through the scientific method, and that's very, very important. It's important to understand. Oh, and Tom, I've started looking into um, zeticism, zeticism, and yeah, that's kind of interesting. Uh, it's just a different method. It's sort of a different scientific, I guess you can call, method where you 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 come to conclusions just based on on observations. You don't sort of uh, look around, make some guesses, and then make observations based on those guesses, and then you correct yourself that way. And I don't know, I haven't given myself enough time to really think too hard about zeticism yet, but I I I like and I'm horribly biased, right? I'm horribly biased towards the scientific method, but definitely gotta keep an open mind about things, and I definitely want to think a little bit more about, okay, don't have this self-correcting um, method. Instead, go out and observe, collect data, and then come to conclusions based on those observations. I don't know. I've got to investigate it a little bit more, but I appreciate the link you sent, because yeah, I think this is sort of where I personally need to start, because I really want to understand. You know, this is sort of in the context of the flat Earth um, hypothesis, theory, whatever it is. Um, it looks like it's fundamentally based on zeticism, and so that's where I personally need to start in order to understand where the flat earthers are coming from. I absolutely have to understand, you know, how are they coming to this kind of a conclusion, and if it's based on asceticism, then that's where I need to start. So thank you for that link. Um, I'm slowly uh, going through um, all of that, and I'm definitely at point zero still, um, with all that. But it's really an interesting concept, and it's an interesting approach to solving problems. So yeah, you know um, I'm you know one of the things that I do is I will bang on things and bang on things and bang on things until I understand them. I this this matter up here sometimes can be as dense as neutron star matter. I mean, things things just don't sink in to this head very well at all. Some things do. Some things do. It's like, oh yeah, yeah, yeah. But some things I am really, really dense on. So it takes me a while, and I've I've learned that, and I understand it. And so my approach is just bang on it, bang on it, bang on it. If I'm determined enough to understand things, I will. but sometimes it takes a while. Sometimes it takes months or years um, to understand things. So yeah, I don't know. Well, I don't know, Tom. You know, science, modern day science, sometimes can be very dogmatic, like religions. So you know, science itself, at least you know, the modern day way of you know how science is sort of seen and used can be you know dogmatic as well. As I've said many times, we all live in our boxes, and you know some of the boxes are really small, and some of the boxes are a little bit bigger, but it's really hard to see outside of that box. um, and that's always my goal is is to you know either expand my box so yeah I can sort of see beyond my my current box, or ultimately you know eliminate that box completely. Now, I don't think that that's really possible, um, because you know at least right now we're extremely limited in terms of you know our senses, um, how how we think, our processes, our perspectives, all of that. So in a certain sense, you know, science can be viewed in sort of a religious way as well. You know, the scientists are sort of the high priests when you have a a question that you want answered. Okay, you go to the scientist, and they will provide you with an answer, and that's exactly that is precisely what has been done in the past with the priests. You know, the priests during you know the 1500s and the 1400s, those were you know the people who knew everything and had the answers. So I don't see much of a difference um, between those two things at all. Um, so you know, I mean, we think that what we've got now is right and correct and is going to provide us with certain answers, and that's precisely what folks back then thought as well. So yeah, i i I think it's what we have now is a different perspective, but I don't know if it's any better. I'm not quite sure about that. So cheers regardless. Di- Dihydrogen oxide tonight. Dihydrogen oxide, H2O. Woo! All right, well, cool. Let's go through archive.org really quick. And I think by then it'll be time to exit this planet. I've got to get some dinner, and then I'm going to go out and collect data for probably a couple hours or so. So let's go over to archive.org. The latest and greatest bleeding edge. That yeah, you know that that news about the galaxy that has no dark matter in it just came out yesterday. So yeah, jumped on that pretty well. So archive.org is updated every weekday, somewhere around like 1 hour UTC. So I'm lucky in that you know I can sit here in sort of you know the comfort of the evening and get the latest and greatest bleeding edge astronomical news, um, hot off the press. I mean, like hot off the press. So let's see if there's anything interesting here. I'm gonna have to I've got a sweatshirt on, and it's getting warm. It's getting warm, so it's feeling pretty nice. So I just took that off because it's getting a little too warm. But let's see if there's anything that catches catches the eye tonight. Cosmic Web Imagers, Super Earths, high energy environment of Super Earth. Next generation Fornax survey. Dense gas, dynamic equilibrium pressure and star formation in nearby star forming galaxies. Improving the accuracy of planet occurrence rates. Okay. Usually there's, at least a couple of dozen new astronomical papers every single weekday, and this just covers astronomy. There's the rest of physics, there's chemistry, there's biology, there's computer science. There are literally hundreds of new papers, bleeding edge, brand new papers, unpublished. These are just the preprints. So they haven't even been published yet. They've been accepted for publication, but that's it. So this is the latest and greatest stuff. Microlensing super Earth orbiting a low mass host star. That's kind of cool. Massive stellar objects in the N66 NGC 346 region of the Small Magellanic Cloud. Just spectra. Okay, cool. Gradient pattern analysis applied to galaxy morphology. So, there are different, what we've observed, different kinds of galaxies, right? There's spiral galaxies, different kinds of spiral galaxies, elliptical galaxies, different kinds of elliptical galaxies, um, irregular galaxies, dwarf galaxies, all that. And so that's the morphology of galaxy. It's just galaxy type. Gradient pattern analysis for measuring gradient bilateral asymmetries uh, of a square numerical lattice. Sounds complicated. Long-lived remnants from binary neutron star mergers. Other ages and masses in the solar neighborhood. Oh, that's kind of cool. T-Tauri stars, those are interesting objects. We should talk about those at some point. Pulsation theory models for Cepheids in eclipsing binary systems. Cool. Cepheid variables are very awesome. Check those out. Those are commonly used as what are called standard candles. We know how Cepheids are supposed to behave, what their characteristics are, depending on how they brighten and dim over a period of time. So if they brighten and dim over a certain period of time, then we can sort of infer things about these stars, including how bright they are. And if we know how bright they are by looking at their brightening and dimming period, then we can know for almost certainty how far away they are. And if we know how far away they are, then the whole universe opens up, because that's sort of what everything is based on. Everything astronomical is more or less based on how far away is it. QPO. I don't know what a QPO is. A quasi-periodic oscillation. Okay. Oh, all right. All right. So they've discovered a 23.8 hour quasi-periodic oscillation in the light curve of the star. So you've probably seen a lot of these weird names of stars, and I call them weird just because that's what everybody else calls them. It's really not so weird, okay? Usually, when you see things like this is designating the position of that star in the sky, right? So what you're seeing here is 13 hours, 47 minutes, 36.6 seconds, positive 17 degrees, 34 minutes, 3 seconds. That's all it is. It's not so weird. It tells you exactly where this object is. And that is very important, right? I mean, it's really, really important to know where objects are if you want to study them. So anybody who um, looks at these things, and I see this often. I see this often, and it's sort of a peeve, a pet peeve of mine when I hear this. They rattle off the name and then say, "Oh, that's a weird name." No, it's not. It's a very precise name, and I, for one, appreciate that. So it is not weird. It's not weird at all. It's exactly the opposite of weird. So yeah, we know exactly where that is. In fact, that's very near the Virgo cluster of of galaxies. I think it's just east of that, east and a little bit north. It possibly is still in the constellation of Virgo itself. But yeah, to call that weird, no. Now, a quasi-periodic oscillation, that's a little weird. But uh, you know, let's see if there's let's let's look and see what they call a quasi-periodic oscillation. Let's dive into the paper. See, all these papers are free. Is it awesome or what? So there's the abstract, which we just saw. And the abstract is just a relatively brief description of the entire paper. It's usually like a paragraph ish or so. But I'm just sort of interested in their observations, and then okay, so let's see. The circle is centered on the position of the X-ray source. Okay, Swift, yeah, Swift. Sorry, Swift is a what is Swift? Is Swift an X-ray telescope? Should tell us here somewhere. Probably is. Yeah, it probably is. I'm not really seeing a description of Swift. Um, but they're talking about it in the context of Chandra, and Chandra I know for a fact is an X-ray. XMM Newton observation detail analysis of X-ray data. Okay, so let's see. These are the observations performed with Swift. So quite a bit of data. This is the number of seconds observed. This is the Julian date and the actual date. So this is old data. Look at this. This is like 10 years old. Just getting around to it now, are you guys? Huh? So 29 observations listed in table 1, performed on between the 6th of February and the 23rd of May 2008. Wow. So they're looking at archived data. Let's just sort of see here. Okay, so here's, wow, that's pretty sparse data. Background subtracted light curve in full. Oh, okay, in the full energy band. Okay. So that's just a broadband filter, I guess you'd call it. That's pretty cool, though. So this is just like a uh, this is what's called a periodogram, or uh, what what I would call a power spectrum, showing which frequencies or are sort of popping out of this data. And as you can see, there's a big spike here, and then there's some other funky things over here as well. But there's I don't know. This is pretty sparse data. I don't know how reliable that is. But there's a definite spike there. Definite spike. So pretty cool though. Let's see if there's any more white curves here. Okay, this is unabsorbed broadband spectral energy distribution. Ugh, I'm not gonna even try to understand that at this point. Black holes. Black holes are another thing that I've always sort of wondered about. Mass spin relation. Get into some modeling. That's all right. There's nothing wrong with comparing stuff to models. You just have to realize that models are guesses. Well, that's kind of cool. Let's see, conclusions. Now confirmed to be spatially coincident with a Seyfert 2 galaxy, for which we have discovered a twin peak quasi-periodic oscillation. Periodic oscillations have been reported for only a few active galactic nuclei in the last years, although they were predicted in 2005. This is mainly because periods are expected to be much longer than for uh, galactic black holes, and most of them can't be observed within a single observation. Twin peak quasi-periodic oscillations are even more rare and are most of the time found in the 3-to-2 ratio. Um, while both of the frequencies of this particular star are a 3-to-1 ratio. Thanks to the theory of resonances from epicyclic frequencies, we managed to provide mass spin relations, which means that a precise value of the black hole mass will constrain the value of its spin. That's pretty cool. So in another galaxy, they're seeing variability on the time scale of hours. So that's pretty amazing. Okay, yeah. So Swift Swift was launched to look at gamma ray bursts, and of course, they see all kinds of other awesome stuff. This is one of the cool things about you know sort of what I call armchair science, is that this most likely, right? This data is available online. So it's archived data. You can go and grab the data yourself, and do the analysis, do some kind of analysis. And this archive data stuff is only going to get more and more and more and more and more. It's already absolutely huge. Lots of discoveries are going on, lots and lots of science, because you need the data. You need that data first, or at least second, somewhere along the line. All right. Well, I think for now I'm going to get out of here. As I said, I've got to get some fuel in me, because I'm going to be observing for at least the next couple of hours. I got some great calibration data. It's probably some of the best I've gotten in quite a while. That's because everything just worked like clockwork. I set up when I was supposed to. I had the camera cooled down. I I was right on top of um, taking my flats. The flats look really good, at least the ones I saw on the screen. I took 3 sets of flats, 3 sets of 10 flats each, one at 1 second, one at 2 seconds, one at 4 seconds. And what I want to do is I want to make the exposure times such that my maximum pixel value is about 2/3 of the dynamic range of the camera. So in my case, my dynamic range goes from 0 to 65,535. So I want my flats to be right around 45,000 counts maximum. That's a nice linear area. Sensitivity is primo um, at those brightness levels. But because the sky, I'm using the sky as my light source, the setting sun makes the sky get darker and darker and darker over time. I think every minute, I think this is true. I I still have to find this out because maybe I'm not exactly right on this, but I think every minute the sky darkens by a factor of 2. I think. I think. So if I want to keep my maximum brightness at about 45,000, I've got to change my exposures. So I take 10, well, tonight I took um, 10 images at 1 second each. And then I took 10 images at 2 seconds and 10 images at 4 seconds. And then I took corresponding darks at 1, 2, and 4 seconds as well. And I take 10 of them. Um, that's sort of an arbitrary choice. I want to get a good sample. So 10 is sort of a decent sample. The more images I can take, the better there, because what I'll do is I'll add them all up um, and um, average them. Average them both in terms of the 10 each, and then I have to normalize those to the exposure times. It goes on and on and on. All right, I'm going to get out of here for now. I hope everyone has a great night and not a and a great day tomorrow. Yeah, that's an awesome name, Swift, because it can slew. Well, if the primary mission was to observe gamma ray bursts, then yeah, you got to be swift. You got to be really swift. You have to be able to make a detection, right, somewhere on the ground, something like that, and then be able to shoot over really quick to catch that thing, because gamma ray bursts, yeah, those things can last I want to say minutes or hours, maybe even less. So yeah, you've got to be swift. So yeah, very cool. All right, I'm gonna get out of here for now, get some dinner, get some photons, and I will see you in less than 23 hours from now. And look, the power stayed on. Yay. All right, take care, everybody. I will see you on the spin. Bye-bye.